Afternoon or good morning. I hope you are doing everything's okay. And actually, I'm glad to be with you for the third time this summer. And I think we are going to continue our issues concerning the seismic interpretation using the automated method of seismic interpretation. And I think some of the questions that have been lighted before about how we can make use of the artificial intelligence and machine learning within our workflow. And actually today I'm just going to fly over some of the these interesting slides concerning the seismic interpretation and the machine learning introduced inside this interpretation itself. Actually, simply on the front view, this slide is talking about the automated interpretation, either for structural interpretation, as you can see on the first workflow, and then stratigraphic interpretation on the next or the second workflow, and then quantitative interpretation on the third one. And actually, the three workflows are considered the main interpretation workflow for seismic interpreter. So we have a seismic interpreter who can do structure interpretation. Another interpreter can do stratigraphic interpretation, and the third interpreter could do the quantitative interpretation. Actually, maybe a few number of interpreter can do the three workflows because actually it's a long journey and it needs a lot of awareness with the technology and a lot of awareness of modules and softwares and so on. But anyway, those are the three interpretation workflows for the three topics, for the structure, for the stratigraphy, and for the quantitative. I think we spent some time talking about structure interpretation, and also spent on the last lecture. Also, we talked a little bit about stratigraphic interpretation, and maybe we highlighted very small about the quantitative interpretation. Each one of them is using what we call it seismic attributes. And I think today we need to elaborate more on the seismic attributes and their role either on the structure interpretation or stratigraphic or even on the quantitative interpretation. So let us have 60 minutes or 1 hour flying over those attributes and how they affect the interpretation and how they are considered sometimes are the best way in order to do a quick and accurate interpretation. When we say seismic attribute, actually we would like to learn more about the definition of the seismic attributes. At the same time, why we are using them and what kind of classification these attributes are. First of all, let us define the meaning of seismic attribute. And then from this definition, we can go why we need to do seismic attribute. So we can go to the usage of the seismic attribute and then how we can classify them. As I mentioned on the first slide, we talked about the structural attribute, we talked about stratigraphic attribute, and we talked about a quantitative interpretation attribute or the interpretation or the QI attributes themselves. Let us define the meaning of seismic attribute. Actually, this is an interesting picture for one of the Middle East, Far East persons from China, from Japan. And if I asked you how you can pick up the difference between a person from China and a person from the United States, as example, then for China you will describe the guy with black hair, with very small eyes, and he's not tall, he's a little bit short, guys, and all of this description are under the name of attributes. So the attribute of the Chinese guy would be likewise the attribute of the Japanese guy. So accordingly, we select the attribute to describe some phenomena or describe some person or describe some seismic. So the attribute itself is a number of characters that can describe that seismic. Simply like this example. Now, principally, actually, I'm going to go back a little bit about the convolutional model just to explain more about the attribute. So actually, the convolutional model of the Earth that start with geological column, and then in between different lithology, as here in shale and sand, and then another shale, another sand, and so on, you have an acoustic impedance difference between them, and accordingly, you can directly calculate the acoustic impedance, which is the rho time v velocity, and rho the density. So the rho time v is the acoustic impedance. When you subtract the acoustic impedance and then you sum the acoustic impedance and then you divide the difference over the sum itself, you can come with the acoustic impedance log like the one in the front view. And actually, at each interface, you can directly calculate the reflection coefficient, which in this case could be positive or negative according to it's just a sign, but it's of maximum 1 or and negative 1. So actually, the RC or reflection coefficient to the right is positive, to the left is negative, and then we can select the value at each interface for the reflection coefficient. Then actually it's come to the wavelet, which represent the source of the sound, or the source of the seismic itself. We convolve this wavelet with those spikes to come up with this nice reflection, either positive or negative 1, to the right positive, to the left negative, or vice versa, depending on the polarity. And then we can those each individual response at each interval of those interval will be convolved together, and we come up with a collective response which will form our trace. This is principally exactly what we mean by convolutional model of the subsurface. Okay. Now, jumping to the attribute itself, actually, we have also to define some important things about the trace itself. Actually, the seismic data can be divided into 4 categories. We study the wavelets or the wave under time or phase, amplitude, frequency, attenuation. Those 4 categories are actually divided principally by Alistair Brown, while actually this is sometimes some of the authors consider that this is not a kind of scientific definition, but actually it at least elaborate in the front of us the types of classification of the wavelets itself. So actually you can study the wavelet post-stack or pre-stack in all in each one of those different categories. So you can study the amplitude post-stack, pre-stack, the frequency post-stack, pre-stack, the attenuation post-stack, pre-stack. So each one of those can be for the wavelet or the wave, we can study either post-stack or pre-stack. Actually, some of the attributes are done on the post-stack, some other attributes are done on the pre-stack. And this is very important to recognize how we can capture each one of them. As example, if we went to the amplitude as example, you can study the amplitude as post-stack, and in this case, you can study your amplitude at a horizon level. So you can pick your horizon and then ask the computer to calculate the amplitude, the reflection amplitude at each trace that you pick. At each horizon you pick, you can calculate the horizon. In this case, you are doing your work post-stack with the data it's already stacked in the front view. Okay, or even sometimes you can pick different amplitude at a window or at a volume, especially when you say 100 mils, 200 mils, up or down at any seismic volume. You can ask the computer to calculate the stack, and it is again a post-stack. Or even you can calculate all the amplitude for all the volume itself, but still it is a post-stack. If you would like to deal with the amplitude at the pre-stack, and this is actually what we're going to learn during the lecture today, using the AVO and AVO attribute, where we need to have the data in the form of pre-stack in order to look at the amplitude pre-stack. So post-stack and pre-stack, both of them are available amplitude study for the wave that we are dealing with. Jump to the frequency. Actually, in most of the cases, the frequency, you have the post-stack and the pre-stack. And actually, for the post-stack, In most of the cases, we are looking at the frequency content, and there is a relation directly between the frequency content and the porosity and permeability and the effective porosity itself during the frequency and velocity as well. So post-stack frequency, we have attribute that represent this kind of attribute. Or pre-stack, actually, we look at the pre-stack for the frequency when we look for the frequency analysis that we do, or the frequency spectrum that we do in order to look at each frequency range before the stack itself. If we want to directly back to the time and phase, and actually this is as example pre-stack, if we would like to look at the velocity before the stack, if we are doing a velocity analysis, we after the velocity analysis, we stack the data, but we can look at the velocity before the stack itself, and this is very important for looking for the NMO, and all the processor know the need for such kind of velocity study. Or actually, you can look at post-stack velocity, or post-stack phase, or pre-stack phase. Both of them are very important. And here in blue, in light blue, there is a lot of attribute that can be related to the post-stack horizon itself. So you have time, you have gradient, you have depth, you have azimuth, you have curvature, you have different type of attribute. If you can catch those blue colors, all of them are kind of attribute. Actually, different softwares got 100 and 100 of the attribute. A lot of the attribute can do the same work, can do the same result. And we have to try on each of them in order to catch the most beautiful one, or the most one that we need to use them, or the most important one that can at least show us some differences on the data. So the attribute application itself is a time of try different attribute at each data, and then select from those attribute the attribute that show some of the data, and neglect some attribute that doesn't show any variation on the data. So actually, for the interpretation domain, you can do you can say structural, phases, pore film, pressure. All of them can be done on the domain of the interpretation domain. Or you can do execution domain using the volume attribute, or trace attribute, or composite attribute. Or another definitions, the focus volume, or the focus domain. So I would like to look for all of the volume that I'm using, or I would like to use a scalped volume from the volume, just small part of the volume, or I'm concentrating on the horizon extraction of the data. So another classification for the seismic attribute in the front view, which is the pre-stack attribute, post-stack attribute, instantaneous attribute, wavelet attribute, physical attribute, reflective attribute, or transmissive attribute. Each one of this definition is on the market, and actually we are using a lot of those 7 categories during our work. So either you can classify the attribute according to structural attribute, stratigraphic attribute, quantitative attribute, or even according to these 7 parameters. By the end of the day, you are dealing with those kind of attributes. For the pre-stack attribute, as I mentioned, it's very important to work with the CDB or within the bin. And actually, in the case of 2D, we are working with the CDB, the common depth point itself, while on the 3D data, we are using what we call it partial stack. We are using the far, mid, and near partial stack, and we will talk about all of this later on. We will pick some of each one, and then we are going to talk about them. Classification number 3 for the attribute according to mathematical, geophysical, or geological. As I mentioned, different classification. Right now, we went through them. We start with one classification, and then the second classification, and this is the third classification. So for the seismic attribute, you can classify them into mathematical, geophysical, or even geological. And then under each one of them, for the mathematical, you can look at statistical one, miscellaneous one, And for the physical, or for the geophysical, you can look at the wave attribute or wavelet attribute. So wave means the whole horizon, the whole trace itself, while the wavelet you are talking with a part, a small part from the wave. Or you can look at geological, where you can study the pattern of the reflector, and this pattern could be structured, stratigraphic, or even you can look for lithological one. So actually, sometimes somebody can feel that the classification of the seismic attribute is a little bit confusing. And actually, there is no one definite correct classification for the seismic attribute. But by the end of the day, you need this attribute to help you on the structure interpretation. You need this attribute to help you on the stratigraphic interpretation. You need this seismic attribute to help you on the direct hydrocarbon indicator in case of the AVO and the quantitative interpretation. We're still on the attribute definition, and this is classification number 4. So you can make an attribute for the trace. You can make an attribute for horizon, just one horizon. You picked one horizon, interpret it, and then you look for attribute to that horizon. You can look for window of data attribute for that window. Or you can look for volume attribute for the whole volume attribute. And the last one usually done in case of looking for structural interpretation. Why you need seismic attributes? Because actually you would like to interpret structure, stratigraphy, lithology, fracture, pressure, or even pore flow. All of this can be done using the seismic attribute. So actually it is essential, and the seismic attribute play a crucial part on the seismic interpretation. It doesn't change our view on the interpretation when we look for the structure attribute. We will see how this will happen even on case of 2D, and in case of structure interpretation, and then in case of stratigraphic interpretation, and last in case of direct hydrocarbon indicator. Yes? Before doing any kind of attribute, the interpreter should go through data conditioning. He should prepare his data for running those attributes. So either he is doing structural attribute, or he's doing stratigraphic attribute, or even in case of quantitative interpretation, he have to make some sort of data conditioning. As example, in the front of you, if you are doing interpretation, the original data as in the front of you in the top section, while the median filter data in the bottom section. So if you are doing seismic interpretation, you feel directly that the section on the bottom is more clearer for the fault itself than the section on the top, because we run some median filter to filter out such kind of noise. You can see that this section is a little bit noisy, but this section is less noise. So you need something like that in the case of the doing seismic interpretation. Before doing any kind of structural attribute, you need to have some sort of median filter. There is a question asking what happened if we don't have 3D seismic. We still, if you don't have 3D seismic, you still can have 2D seismic and run the same filters on them. If you are asking about filter, you can filter either 2D data or 3D data, and you can do a lot of many things on 2D data. Not all what you can do on 3D data, but still on 2D data you can run some of the attributes on set. We will see some example on the next coming slides. Again, here's filter of the frequency, as you can see from the top, original data, and then median filter, and then frequency filter. You can see that you can highlight some stuff, and you can, in other words, you can look for another stuff to hide, to look at the. All of this you should play with before you work directly with the data. So. Another example for the attribute is the dip and azimuth, and all of us knows exactly what is the meaning of dip and azimuth. and actually on the computer just calculate the depth, direction, and amount for the dipping of the seismic data. And if you are using, you can apply this for all the volume. You can apply this for just a part of the volume. You can apply this just along your structure or along your peak to horizon to come up with dip and azimuth. And actually, you can color coding dip and color coding azimuth with different range of code, and then join them together, the dip and azimuth. And in this case, you can come up with very interesting feature, as you can see on the right, left, right on the hand side, where this color, those two color together, and this is time slice on one of the attribute, the structure attribute, and it is posted with the dip and azimuth, and you can directly look at the color and see which areas have fast dip and in which direction as well. So it will help you a lot in interpreting the data using the dip and azimuth. Jumping to a third attribute of the structure attribute, rather than looking for the dip and azimuth, is looking for what we call it curvature attribute, where the system can directly calculate the curvature of a surface as a line. So as an example, you have an anticline, you have syncline, and then you have a straight surface. And if you just imagine that you have a ball and you throw this ball from here, yes, from left, the ball will go from down to up, and then it will goes down, and then down, and then it will goes up again. And actually, the role of this ball actually will calculate for you the curvature of this surface. Will tell you that this is an anticline and this is an syncline, mathematically syncline, and this mathematically exactly what you need. And then it can put in the front of you a volume for the curvature attribute, telling you where the anticline, where the syncline, sometimes where the channel itself, very important sometimes, the curvature attribute. So the curvature attribute can tell you actually where the syncline, the anticline, where the channel, because the surface of the channel itself can be considered like a curvature surface itself. As you can see on the front of you, all of this small twins can be looks like something that can be detected using the curvature itself, and even the anticline can be detected with the curvature attribute. Yes, and actually there is different kind of curvature, either 2D minimum curvature, maximum curvature, Gaussian curve. All of them are different types, but actually we are giving most probably the same exact shapes. I'm going to run off this, and I'm going to show an example very interesting about the curvature attribute. And this is a real example where there is an anticline, nice anticline in here, and actually there is a nice anticline also in here. And the main target actually with the deeper one was that deeper one, and actually this was the highest position on that seismic section for that reservoir. And the well have been drilled. This is a real story. The well have been drilled to that reservoir, and it came positive. It came positive. It's a highest position structure. But actually, on the top of this reservoir, there was another reservoir, which is ARE reservoir. And as you can see, very nice separation of about 60 feet or 65 feet of very nice oil leg in here. And actually, this after the drilling that well, and another well was drilled in order to develop this interesting 60 feet on ARE. The next well, so well one, come up with this 65 feet. The next well come up with only 5 or 10 feet, almost less than 10 feet of the reservoir. And a lot of interpretation have been done, but a first interpretation assumed that there is a fault, because the wells are the two wells are 380 meters from each other, and very interesting that this thickness of 60 feet disappear in just less than 400 meters, and actually there is no any indication for any faults around the area. And then actually the exercise have been run, in order to run some of the attribute in here. And we run the attribute and in case of the data in the depth domain, and we run the curvature attribute. And the most interesting feature of the channel system that was trending in here was hit by the well number 1 and become a positive. Yes, while just the next well have been drilled in here, and this is about less than 400 meters between the two wells, and this well just come was 200 because actually it's out of the channel itself, and the channel is very clear mapped by the curvature attribute itself. Actually, and this is the attribute done for the curvature itself, and this is exactly the channel itself. So a third well have been assumed to catch the extension of the channel itself, and they have been drilled, and it came actually, as you can see it in here. And this is well number 3 on the channel direction that have been defined by the curvature attribute, and it came exactly almost with the same thickness like the first one of the sand. And this is actually a direct impact from the curvature attribute, which is a one of the structural attribute. Yes. A third example of the seismic attribute, which is the spectral decomposition. Actually, the spectral decomposition have been introduced by BP actually since almost more than 20 years ago. And the philosophy of this attribute is to look at the interval of the data that we are interested in and that we are learned from the regional geology and from the history of the area, that this interval is undergoing some sort of channelizing system or burgrading system or any kind of the stratigraphic blaze. So we define this interval first from in our data, and the principle of the spectral decomposition comes from the word of spectral decomposition. So spectral analysis means we are going to look at the different frequencies spectrum themselves within our data. And decompose, it means that we, rather than we have the spectrum composed together, we decompose that spectrum and look at each single frequency. And then actually we see how our data is sensitive to which kind of frequency. So say I have frequencies from 10 hertz to 60 hertz, so 10, 11, 20, 11, 12, and so on until 60 hertz. Then we test each one of these low frequencies, the amplitude of each one at that interval, and from that we can integrate one or two or three of those frequencies that we felt from testing our data that it does produce the stratigraphic feature into our eyes. And actually, the Nigel Anstey, this guy from IHFC, was the one who leads at the first when he said that sands and shale are very near to each other and have overlap between each of them. But actually, when you send a wave into the sand and shale, each one of them will reflect some kind of frequencies that are different than the other. So the sand would reflect back some frequencies, while the shale will reflect another frequencies. If we were able to differentiate between those frequencies by color coding themselves, then we can differentiate between sand and shale. And so in this case, we can differentiate with other clastic as well. And at the same time, we can pick up the shape of the container of this sand and shale, which in most of the cases is the channel that we are looking for. This is principally the principle of the spectral decomposition itself. Yeah, how they do it? They do it with a very interesting way, where, as I mentioned, they look at a window, and at that window, we decompose the frequencies in here by the software itself, and then we look at the different frequencies that represent most of the data. As example, in this data, we have the 15 hertz, the 25 hertz, and then the 35 hertz. Each single frequency of those single frequency got the maximum amplitude on the data. Then we need to color code each one of these single frequencies by a unique color. So as example, we will color the 60 hertz in an example. We'll color the 60 hertz with red, the green with 50, and the blue was 40. In another area, you can find it, no, it is 15, 25, 35. It's different. So each area got the different frequency highlighted. Then we can use the red and the different magnitude of red for looking for the amplitude of the 60 hertz. And then we can use green, the different magnitude of green to represent the 50 hertz. And then we can use the blue for the 40 hertz. Then actually we can put them together, blend them together by what we call color blending in order to see the very nice picture in the front of you to the left, where you can see directly in here this nice distributory channel on the subsurface of the data. And actually this is a time slice from the volume itself that we mixed the data. So this is not slice from the seismic data itself, it's a slice from the data of mixing only three type of frequencies, 40, 50, and 60. And we use this to pick up this geobody. And actually you can go up and down with your slide and bring this geobody into life, and then export this geobody. By this method, you are exporting the container that contains your sand and contains your shale at the same time. So the spectral decomposition is one of the most important one in mapping stratigraphic play on the subsurface. Now let us conclude what we have learned. We have learned some structural attribute like depth and azimuth, and then we looked at some another attribute, stratigraphic attribute that we looked at them, which is the spectral decomposition. We will continue looking for the attribute just to let you be aware, and this is actually going down from the top of this reservoir to the bottom. Each one you can see how the difference lay off of the channel itself. This actually published by BB about more than 20 years ago. This is another time slice for the spectral decomposition for 10, 20, 30 hertz color blending between the red, green, and blue. And you can see how a kind of very nice art that comes from the subsurface, where you can see the channels in many areas, and the footprint of those channels. And also, in addition, actually, you can see the echo of some of the fault as well. You can see how the fault is playing, the different kind of fault in there, and also the channel systems. Okay. Now we are going to talk about another very important structural attribute, which is coherency, or sometimes in other software you can find the variance, which is more or less they are two sides of the same coins, the coherency and the variance, in both of them. The coherency actually looks for the if you are looking for similarity in case of you're thinking mathematically, or you are looking for continuity. So if, as example, you are looking for the strike of a fault on the time slice, so the strike of continuous lines will show a continuous strike of a fault will show a continuous line on the strike of the fault on the time slice. This is very simple. And actually, the measure of trace-to-trace similarity of the seismic waveform within a small analysis window can look for what we call it coherency. Let us go. So this is an example for coherency. So this is a cross-section showing the fault itself. Yes. And then the computer will look for the coherency of this reflector, and then stop, and then coherency of that reflector, the same reflector, and then stop. He will look where the coherence is, and this termination is represented by this nice black line that represent the strike of the fault itself. So all of this black lines on the time slice of the coherence time slice is reflecting the strike of the fault. So you can directly conclude your strike of the fault just using the coherency itself. Actually, the coherency have been done for the first time from the AMO command, calculated the coherency. Then the variance, which actually, as I mentioned, it is the side, the other side of the coin, where you are looking for the difference not the continuity. The difference between them, the continuity. So coherency looks for similarity using cross correlation and the average over the interval, then infer to similarity. Variance measures the difference from mean value, so it is direct measurement instead of the intermediate step. So it is a kind direct measurement to the direct change itself. Actually, for the variance and coherency, to the left-hand side on this slide, you are seeing variance. To the right-hand side, you are seeing coherency. Both of them are producing most probably 80-90% the same conclusion about the fault strike. This is time slice in coherency, this time slice in variance, and you can see directly these nice black lines representing the fault, and you can see that those faults are more or less more sharp in case of the variant than coherency. But actually, I'll tell you what, some of the software can do coherency, some of them can do variance, but most of them are doing more or less give you the strike of the fault on the time slice itself. Yes? The sweetness, this is an interesting attribute, which is the amplitude divided by frequency. So this is exactly what they call it sweetness, which is at each sample you get the amplitude of that sample and then divided by frequency of that interval or that sample, and then you come up with a very nice color, as you can see to the right. So this is normal section in A, and in normal section you have 1, 2, 3. You have high amplitude sand, 1, 2. So you can see them directly on the on that interval, while all of the shale is low amplitude. Yes, and then you have very nice sequence, high amplitude sequence boundary at this one and that one, and then actually when you have time slice on that area on B to look at this interesting sweet point, you can see it comes from point bars. The point bars area. Actually, this is exactly sweet spots that comes from the sweetness itself. It's important sometimes to run the sweetness, and you come up with some stratigraphic interesting feature on the time slice itself. Okay, now we have looked for mix between structural attribute and stratigraphic attribute, and we felt how important the application of the structural attribute in defining the strike of the fault on the time slice. And actually, the more important is to use and integrate this while you are doing interpretation. So you do the structure. If we went back to this slide, let me just. If we went back to this slide, this is your inline, or this is your cross line, and this is your time slice. You have to have all of them together while you are doing interpretation. So it will tell you that this stick is belonging to that strike. There is another stick. Maybe this stick is belonging to another strike. So you can connect the sticks with the strikes responsible for those sticks all over the volume, so you can interpret the data in a real 3D data rather than the normal making of putting your sticks only on your inline or all your cross line and then tie them together. So using the attribute in such cases will help you to interpret your data in a very good method and very accurate method as jumping to another kind of attributes, which is instantaneous attributes, which can be done sample by sample on your volume, like phase, as example, which is description of the phase angle at any instant along the trace. So along each sample, you can calculate the phase angle itself, and then you can color code this angle. And it's very important to use this attribute in case of termination. As you can see on the deeper stuff here, you have main horizon in here, and then you have on lap going from right to left, or even on the below surface, you can see the angular unconformity termination. Actually, the instantaneous phase is very important in case of picking the terminations itself. And actually, it's very good also in picking some of the fault, as you can see, also because it looks for termination on both sides of the fault itself. This is what we call phase section. It's a one of the instantaneous attribute. The frequency or instantaneous frequency, it's also very important for looking for low frequency interval that sometimes associated with gases, because usually the interval of the gas is characterized with low interval velocity and low frequency. So this will lead to a help on looks for the hydrocarbons anomalies that pretended to gas. The amplitude, of course, the amplitude have a very wide range of attribute. So we have reflection strength, we have RMS amplitude, we have maximum amplitude, we have average or absolute amplitude, we have what we call it total energy. Each one of them, if you are interested, you can look at the description on your geophysical dictionary to learn more about them, or you can look actually to Schlumberger SLV site. They are describing all of this in a very good manner. Each one of them is representing the amplitude itself, and you need to look for amplitude because it is very usable. As example, the amplitude the reflection strength is the best amplitude measured for most purposes. So the reflection strength, this is very important. Can be computed directly by your computer very easily, either through to a certain interval, or through a surface, or even through the volume, the total volume. Together you can look at them. You can also total envelope of energy at any instant. You can look not only for your amplitude, but the envelope that as the red one, that will tell you exactly where are the highs and where is the lows of the amplitude. Usually the high amplitude is with either with lithology change between shale and carbonate, or the amplitude sometimes come from directly from gas, sand as a high amplitude. This is with field classifier. We're not going to show you, but at least I'm going to show you something like an interesting on the amplitude map that comes from sand to the left. This is a very nice time slice, actually, and it shows an interesting canyons, submarine, and then it goes to basin floor, very nice basin floor fan, and you can see the echo, the footprint of the seismic, these lines. This is the echo of the seismic data acquisition, but at least it is give you the morphology of the model itself of have canyons, and then you have basin floor fan, and you can see the high amplitude of the sand, and these nice little bullets are the wells that are producing from the sand, and you have another wells that producing from the canyons, and even from the side of the canyon, some are producing. As you can see, the amplitude is very fantastic. Art comes from just putting an amplitude map. Yes, still you can see a different level. Now I just flow with you to just show you how the attribute is very important for you as an interpreter, either if you are doing structural interpretation, or are you doing stratigraphic interpretation, or like what we are going to learn now here, if you are doing direct hydrocarbon indicator directly from your data. Let us see here. Are you okay, guys, or you would like to get 5 or 6 or 7 minutes? Then we can come back to the AVO and direct hydrocarbon indicator. Let me know. The coordinator, can you reply for me? Are you okay to take 5-7 minutes or so, or we can continue?
As you like, Dr. Ali. It is up to you.
I have no problem. Sometimes if you're talking more than 45 minutes, it gets harder to the audience to listen. So if you wish, you can get. It's almost in our time. It's 10 to 6. Let's get just 7 minutes or 5 minutes. and then I'll come back directly to answer the three questions, then we'll continue.
Okay, so we will have a break for 7 minutes. So
Yes.
please, the attendees, please write your questions, leave your questions in the Q&A section. And after 7 minutes, Dr. Ali will come back and start answering them one by one.
Yes,
So
then we'll continue with the different stuff. Yes.
yes, so please, if you have any questions about today's lecture or maybe last week lecture, you can leave it here. And after 7 minutes, we will continue the lecture and answer your questions. Please, if you have a question, write it in the Q&A because I see some question in the chat. Please don't write questions in the chat. Write your questions in the Q&A section, please. Olusegun, you wrote two questions in the chat. Please write them in the Q&A. Please write your two questions in the Q&A section, not the chat. We will resume the lecture after 2 or 3 minutes maximum. We will resume the lecture.
دكتور احسن، انا جاهز على طول. اوكي. Okay, guys, can you hear me?
Yes, sir, we hear you.
Okay. And can you see my screen as well?
Yes.
Okay, let's answer the first questions that comes from, please, from one of the gents. Please, after applying the volume attribute with you do the interpretation on the attribute volume or the original seismic volume? We are using all of the attributes that we need directly. In the front of you, as you can see, the time slice is showing the variance or the coherency come from the coherency attribute, and while the vertical section is from the seismic itself. So I'm putting here a display between time slice from the variance and cross section or inline or coastline from the seismic data. I'm going to show you how this will work in a live session. As you can see, I'm referring here to the fault stack vertically from the seismic section, the vertical seismic section, inline or coastline, and then with different seismic section, all of those green lines representing different seismic sections, and all of them aligned on the strike of the fault. In this case, you are doing a real 3D interpretation. You are using 2 volumes at the same time. You can use more than 3 volume, 4 volume, depend on whatever you'd like to together. And you are doing your interpretation on the real 3D environment, not using the seismic section separately and the time slice separately. In this case, you are looking for each single fault with each sticks for that single fault with single color of that single fault, and you can see the fault sticks on the seismic section, and you can put the fault strike on the time slice at the same time. Hope that this answered the questions that we talked about. Now, the second question, can spectral decomposition attribute be done using post-stack or pre-stack data? Actually, in most of the cases, we are using the spectral decomposition on the post-stack data to look for all the ranges of frequencies on the post-stack data. But you still can run spectral decomposition on the partial stack of the 3D or either far offset stack or near offset stack or even the full stack of the 3D itself. So it could be done pre-stack or post-stack, but on most of the cases, the spectral decomposition is run on the stacked data. Question number 3, how can you identify the frequency of the seismic data? This is very simple. All of the software can tell you exactly what is your frequency range from the seismic data. At the same time, if you have a software that can calculate the spectral decomposition as a software, you can directly use it. As example, it is used isofrequency in case of Schlumberger, or spectral decomposition. If you are using Hampson Russell as example software, you can directly identify the frequency content, and you can divide even from, as example, from 5 to 10 hertz, from 10 to 15, from 15 to 20, until you reach the maximum. If the maximum is 60, as example, you can look at each 5 segment of hertz separately, and then you can select from those even a single one. So as example, from 5 to 10 hertz, you have 5, 6, 7, 8, 9, and 10. You can look at the 5 separately, 6 separately, 7 separately, and so on until 10. And then you can select from them 1 or 2, whatever, in order to blend them together into the different color. So the selection of the frequency is within the software. It's enlarge you of this. It gives you this opportunity. Another question: which of the attribute is more suitable for imaging fracture? This is a good question. And the bugs in carbonate reservoir. Actually, there is a lot of attributes, but the main one that's very important is variance, is one of the most important. Coherency, if your software is doing coherency, also is very important. Chaos is the third one, and for Schlumberger, the ant track attribute. The ant track is one of the very interesting attribute that you can use it for inferring the fracture themselves. Nowadays we are using the artificial intelligence also as well together from those attributes. We would use all of those attributes together and they come up with some sort of artificial intelligence to look for the attribute. And I think on the last lecture we have highlighted how we can do that for detecting fracture. The last question: what is the concept of seismic petrophysical inversion? Is the study different from the conventional seismic inversion? The answer is yes. They are two different directions. When we are doing conventional inversion using the low frequency model from the model, and the seismic from the seismic data, we are doing seismic inversion for the whole body. While actually, if you are using the AVO attributes, which is the far offset and near offset, and you are doing a full inversion, that we call a full wavelet inversion. In this case, you are doing a very detailed work. Since you are going to look for porosity, you are doing for water saturation, so you are going to look for petrophysical parameter, which is different than the simple way of the inversion of the seismic data itself. How do you do the interpretation if you don't have inline? How do you do the interpretation if you don't have inline and the cross line in a 2D seismic? In 2D seismic, you are doing your interpretation using the 2D lines and your map. You don't have the opportunity to put everything in a 3-dimension and look at it. And this is the shortage of the 2D. You are interpreting line by line, but you can use the visualization of the software itself, but you don't have data between the 2D lines. So you are restricted to the intersection between 2 lines, and this is your maximum limit. So you cannot add any more. If you don't have 3D, you cannot add any more actually. You restrict your data to the lines that you have. You can consider them sometimes you are looking in 3-dimension, but while it is not, because the distance between the parallel lines or the cross lines that are perpendicular to each other in case of 2D data is large distance. It's not 25 meter or 50 meter as in 3D data. Hope that this answer all the questions that you have. And maybe you can come back to the last part in our lecture today about the pre-stack. Let me start with this and bring it over. Now, can you see my screen?
We see your screen, but it is not in a presentation mode.
But now it is. Okay, let me share new and come up with this and share it. I think now it is.
Yes.
I think now it is. Yes. Okay.
This is a AVO
Concept, the AVA concept. Yeah. Let me put my pointer as laser pointer. Actually, just give you some information about the AVO concept itself, which a kind of attribute, but pre-stack attribute that we needed to have it in here. And actually, this concept is very interesting because actually, when we shoot our seismic, as you can see, between S1 R1, S2 R2, S3 R3, and last S4 R4, the distance between source and receiver is larger as you go from offset 1 to offset 4. And usually when we collect our data, we would like to stack all these 4 ray paths together into one assumed vertical ray path, which practically cannot be done, but we do it according to some definitions in there. And actually, you should have the high amplitude for coming from this point, the common point, at the nearest trace. And as you go away from the center, then the amplitude decreases, normal decay of the amplitude itself. But actually, they found a very interesting feature. They found that this amplitude increases rather than decreases in case of what? In case of the presence of gases within the sand. If you have sand and this sand is sandwiched in shale, and there is a gas on this sand, the response on the amplitude is different than the normal response. It does not decrease by distance, it increases by distance. And the owing to this response to the presence of the gas itself. Let us think about this, how it happened sometime. Actually, when you throw the stones over the water, when you are at the beach and you throw a stone over the water, then your stone will jump and then go up and then jump and go up until it sinks down. And actually, if you throw the same stones vertically, it will not do the same. It will directly sink down into the water. This is because of 2 things. That the response of the water is different than the response of the rock, as example. If we imagine that we change this water into a rubber, elastic medium, and then we throw the stone will never do skipping along the surface of the rubber itself like what it did within the liquid or within the fluid. That's because the property of the fluid is different than the property of the elastic or the rubber itself. When you put a fluid inside the rock, it behaves differently than it's a pure rock. So when it's a pure rock, it will behave like rubber. So that's why we call it elastic properties of rock, because the behavior of this rock with the sound waves is like rubber. So the rubber and the rock behave the same. While the fluid, if it is water or another fluid, gas, or even if it is oil, it behaves differently. Then when you engage a fluid inside the rock itself, the rock change its behavior, and it behaves like mixed change, not like exactly the rubber change. And that's why we get what we call it amplitude versus offset. The amplitude increases a little bit versus the offset, and they took this as an indication for the presence of the fluid within the subsurface. If you go down, actually, on the slide itself, to the left-hand side, we have what we call it far offset stack, and then we have near offset stack, and then we have full stack. This kind of data, we stack the data from the distance that near, say, 2 kilometers, and then for the far offset is 8 or 10 kilometers. and then near offset is 2 to 3 kilometers, and then full offset from all distance away from the point itself. And you can see that for the far offset, we started to have an echo for the contact of coming from a gas, horizontal event, you can see it in here. Now, while for the near offset, you cannot recognize, or it's not easy to recognize this flat shape, while on the full offset, there is nothing at all. And this tell you what, that the detection of this contact between fluid and the rock itself can be detected using the far offset stack. If we looked at the far offset in case of the 3D, or if we looked at the far traces if we are looking for 2D. And from that, we come up with the concept of the AVO itself. And many scientists have worked on that. I'm not going to talk too much about that, but I'll jump directly to how we can differentiate this on the data. And I leave the mathematical concept for you guys. In order to learn more, I can give you the sources of this concept. As example, I'm going to give a nice example. This example has been given by Hampson Russell many times. This is CDBs, and this is from 2D data. This is CDB 326, 327, 328. So this is CDB 328, and from 40, as you can see here, this is the distance itself. So and this is the interval that they are interested on that interval, and you can see or notice that the amplitude here are increasing as you go from left to right. From 40 to 680 distance, it increases. The amplitude increases. And this is before stack, but after doing the velocity analysis, and you are ready to stack them. So we did all the processing of the data until we reach the velocity analysis and NMO correction and the muting, and then we are ready to stack the data. Before doing these steps, we look at the data, and we notice that there is a difference in the amplitude between the nearest trace at 40 and the farthest trace at 680. Yes? If we color them, then you can look that, yeah, it does have interesting color on them, showing that there is something happening there. Okay, from that, we get rid of the peaks and the trough, and we choose this CDB. This is the CDB that we choose them, which is 328. We choose this CDB, and we get rid from the peaks and troughs, and we kept only the wiggles. Yes, there is 9 traces. If we count the other time, the number of traces, this is 1, 2, 3, 4, 5, 6, 7, 8, 9 traces. Now we just zoom on them, and you have 9 traces from left to right. And then, as you can see, we can look at that interval. This is low amplitude, while on the trace number 9, it have high amplitude. So we notice that there is change in the amplitude laterally. But we would like to capture this kind of change of amplitude and see if it's an indication for the presence of gas or not. So what the computer will do, this exactly our traces. Well, we will digitize this. So we'll take the first trace from those 9 to this is number 1 of 9, and then we will get to samples them. Each sample, we will calculate your amplitude. To the right is positive, to the left is negative. As you can see, this is negative, minus 10, minus 18, minus 11. This is right, so 18, 48, and so on. So we can change the shape of our trace into numbers, either positive or negative, representing the amplitude itself. So I have the number of samples, say sample number 1, sample number 38, and to the right, you have the amount of amplitude, either positive or negative. We do the same for the next trace, the third trace, the fourth, the fifth, the sixth, the seventh, the eighth, the ninth. So I will have digitized the ninth trace until trace number 9, and then we come up with 9 columns. Each column of this column represents the amplitude vertically from the sample number 1 to the sample number 38. Of course, in the rare cases, the sample is not going to end with 38; it's going to end with a large number. But at least you have number that refer to you either it is positive or negative amplitude, and how the maximum. Directly, I can tell you that there is minus 71, very high amplitude here, negative. Yes, and also there is sometimes another lowest one. So this is highest, this is lowest. Now, what the computer will do? Actually, the computer will do a relation between the amplitude vertically positive and amplitude negative, and then on the horizontal one, we are using the reflection of angle. It is either 10, 20, 30. There is direct relation between the angle and the distance. As the distance between source and receiver increases, the angle increases. So you can say that the nearest traces have small angles, the farthest traces have largest angle. So you can relate those into a relation between the angles, and there is some sort of very complex equation for Zipret's equation that ties this relation to each other, which is the angle and the reflection coefficient. Yes, the reflection coefficient in positive, reflection coefficient in negative, and the angle. And then with a linear regression, you can directly relate those. So the blue line represents the digitizer for you. It took the first sample, and then it will get the first line reading. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the digitization of the first one with the value itself plotted on that graph. Then you can, with linear regression, tie them with a kind of linear regression in them. Then we will move one step from first sample to second sample. If you just follow this blue lines, it represents the digitizer. Yes, this is the second, the third, the fourth, the fifth, and so on. With each sample, it will represent a kind of linear regression until we reach the sample that we are interested in to see them. Here you go. I think here you can directly see on this one, or even the one before it, you can see that my digitizer is telling me that here is the lowest negative amplitude, and here is the highest negative amplitude, and there is an increase on this amplitude from left to right. This is represented on this relation, on the graphic representation, as data started negative in here and ended with data more negative in here. So this kind of relation at the simple regression can be, rather than being simple, can be like a graph coming from low negative to high negative amplitude. And in this case, this is a kind of representation for the presence of the gas itself. Actually, they call it this class 3, and there is another 3 classes at least in different in the market: class 1, class 2, class 4. Class 3 is the ideal example of the bright spots, or the ideal example for the presence of gas immersed within shale and continue within sand gas itself. And it can directly on this relation give you this nice negative value increasing to more negative. Actually, most of the other classes can be shown in with the same method, but you have to learn and to teach yourself how those FARs are represented. So I'm gonna skip this because actually it is more or less time consuming, and then I'm gonna show you directly how we cross plots this. So we have what we call it, this relation between let me come back. The relation between this linear regression will give you the cross part, the intercept part from the vertical, and the slope. Both of them, they call it attribute, or they call it AVO attribute, and they call it the intercept and slope. So the slope is one attribute, and the intercept to the vertical is intercept. So using the intercept of, and slope, both of them, we can even go more and look at them. So we put the intercept horizontal and the slope vertical, and then we can use our digitizer to plot each sample reading of the amplitude in them, and then it will end with a very interesting shape where actually it will tell you that your your interval is belong to intercept, and this intercept and this slope, where you have maximum negative and you have maximum negative on both the slope and the intercept, which is maximum negative in case of the amplitude itself, and you can select this interval, and exactly the computer can define this for you. If we succeeded to do that, we can invert this data and use what we call it inversion for the far offset and the near offset, and look at the effect of the gas itself. Not only this, but actually we can calculate what we call it the water saturation. We can calculate what we call it the effect of porosity of coming with this interval. All other rock properties, they can do it, and in this case they call it inversion for the AVO attribute. This is conclude very roughly and in very fast manner what we mean by the seismic attributes. All of the AVO is done on the pre-stack. So in case of 2D, it will be CDB. In case of the 3D, it will be partial stack, far and mid and near. This is a part called pre-stack attribute. While the post-stack attribute, we went through them either its structural or stratigraphic attribute, or even sometimes mix between structural and stratigraphic. This is it for today. And if you have any other question, let me check if. I don't think that we have another question, but I'm ready to answer any question.
Thank you very much for everybody. Dr. Ali, please enjoy your evening and have a wonderful evening.
Thank you very much, and happy to be with you all the time. Have a good day.